So when we were doing our hypothesis testing, we didn't treat them as two totally separate groups. We created a third group, which was the difference between them. And the hypothesis we were testing is that there's no difference versus there is a difference. Today we're looking at independent samples, and we can't do it the same way. The reason being, maybe the easiest explanation, if I have two totally independent samples, they may not even have the same number of points in them. They could, but they don't have to. And so if the first set had 15 points and the second set had 20 points, could I go through and find the difference between all of them? No. And those differences wouldn't mean anything. If I'm just taking a random hotel price in Monroe City versus a random hotel price in Dallas, and the next one is Hannibal and New York, and if I'm just subtracting random points, that number doesn't meaningful. So when we are doing this, we are going to treat them as two totally different tests. And we're still talking about the mean, so if we're doing anything involving the mean, what kind of testing are we doing? T-testing. But the difference is we have two samples, so on our calculator we are going to be using the two sample t-test. We're telling it it's two separate samples, treat them separately, and then we're going to compare them at the end. Alright, so this, I'm not going to go over this a whole lot, but the calculation, your calculator does it all for you. We're used to finding a t-score, which is R value minus the mean divided by standard deviation, right? What it's doing is taking the two separate sets and subtracting their means. The mean of the population is the difference between those individual means. Standard deviation is from the two sets combined. So it's a more complex formula, but we aren't doing them by hand, so it's not overly relevant. The big thing you have to realize is criteria. If we're dealing with a mean or a t-distribution, what criteria have we been using the whole time? We either had to have normal data or n had to be greater than 30. That's still the case, but now for both sets. So both sets of data have to be normal, or both sets have to be bigger than 30 in order for us to assume that. And then if that criteria is met, we're able to do our test. So we still have left tail, right tail, two tail. The null hypothesis looks a little bit different from yesterday. So yesterday we were assuming no difference. And it's similar here, but since we're keeping them separate, we're not looking at the difference. We're just going to say the mean of the first equals the mean of the second. So saying that there is no difference is like saying they have the same mean. Then the alternative is the mean of the first is greater than the second, less than the second, or not equal to the second. We'll have an alpha. We'll use our calculator to get our t and our probability, and just like always, we reject if p is less than alpha. So let's just go with an example. So a researcher wanted to know whether state quarters had a weight that was more than traditional quarters. He randomly selected 18 state quarters and 16 traditional, weighed them, and obtained following data. So before we do anything, before we even enter this in the calculator, can you tell me, why is this not matched pairs data?
15 and 18 and 16.
Okay, big clue is they're different sizes, so they can't be. Why else would they not be paired up in it?
Doesn't matter where the state comes from.
Yeah, it's not like I took the Missouri state quarter versus a regular quarter and compared two quarters from the same state or anything. There's just a random collection of quarters. So these are totally independent. Because they're independent and they're not ordered pairs, that also means when you put them in your calculator, if you get one out of order, it's not a big deal, where it was before. So go ahead and enter all the state quarters in L1 and the traditional in L2. The null and alternative hypothesis. So the null, since they're separate, we're not looking at the difference. It's just that the mean of the first equals the mean of the second. Alternative, what am I trying to decide?
Greater than.
Right, if the state quarters have a mean that is more than. So just so we're consistent, the first thing in our table is always going to be number 1, the second thing is number 2. Okay, so if I want this one to be higher, I'm testing if the mean of the first is more than the mean of the second. Okay, so now on our calculator, we go into staff tests. We cannot do the t-test like we have been doing because it's going to ask us which list, and we have 2 totally separate lists. So we are going to go, which one would you guess? Number 4, 2 sample t-tests. Alright, so now we have to make sure it's looking at the correct stuff. Sometimes I might have the points to put in. Sometimes we might have to read the problem and find the data. So it's based on if we have the data and stats. This time it's the data. List 1 should be L1, list 2 should be L2. Frequencies are always 1. We don't touch that. We are testing if the first is greater than the second. Cool. We have not talked about that, but make sure it is set on no. And then calculate. So a lot more stuff here, but we're really just flipping through it all. And so we get a T of 2.5. Our probability is 0.0086. If you got a number very close, that probably means you mistyped 1 point. It doesn't take much to throw this off a little bit. And then we look, alpha here is 0.05, so what does that tell me?
You're just gonna
Reject. Okay, the null hypothesis is that they were the same. So if I ask you to write me a sentence explaining what this means, there is evidence to conclude state quarters way more.
Would you be okay if we said to conclude the alternative?
Alright. Questions there? We can use the confidence intervals on these as well. If you're doing them by hand, the calculation is much more complicated, but we don't have to do it by hand. Our calculator can do it for us. So let's take a look at the same one. If I wanted to make a 95% confidence interval about this, so we look at our tests. We're used to just doing a t interval, but we have more than one sample, so if we go down 0, we have a 2 sample t interval. So same labels, we're used either t-test or t-interval, so the only difference, 2 sample t-test, 2 sample t-interval. Again, we have data, list 1 is L1, list 2 L2, all got the same confidence level. I said 0.95. Pool should be no, and calculate. Okay. The only difference is when we go to try to decide if I were using this to decide if I rejected or failed to reject my null hypothesis, it's a little bit different because we're used to just looking at our null hypothesis and saying, okay, is this number in my interval, but I don't even have a number here. We've built a confidence interval for the difference in the means. So if they're truly the same, what should be the difference between them?
0.
0. So kind of like yesterday, you're just looking, is 0 in my interval? It's not, so we have evidence to believe it's Any questions there? I just want to show you one thing on your calculator. So we went like for the t-test, the 2 sample t-test, number 4. If you didn't have data, if you had the stats, it asks you a lot of questions. It's the same ones we're used to putting in, but we have to do it twice because it asks the mean of the first, standard deviation of the first, and of the first. And then the same thing for the second set of data. So if you have to enter that, your problem has to give you all that information. And then you enter it all in and test it like normal. Any questions there? So my plan, I really wanted to just let you work on this homework today. Tomorrow I wanted to just take some time when I start putting all these problems together, making sure we know what strategy to do when, so we're really just practicing as a